All right, we are moving on to chapter 4, and 4.1 is exponential functions. So, an exponential function is a type of transcendental function, transcends algebraic functions like plus, minus, um, multiplication, division, powers, and root. Now, the variable is going to be in the exponent, not the base. So what does that mean? That's, for example, we'll have f of x equals 2 to the power of x. So you see the x is in the exponent. And then compared to if it's um, the base, it would be f of x equals x to the power of 2. So here the x is the base. For this one, 2 is the base, and the x is the exponent. Um, Also, the exponential function shows a pattern of growth. And if we quickly just sketch um, an exponential function that shows the growth, it looks something like this. Now, our other option for the pattern is decay. And the decay, this one's the harder one to graph, comes down like this, something like that. So that's our decay. Now, notice that they do have the same y-intercept, which is 0, 1. And then there is a horizontal asymptote y equals 0. Now, the inverse of an exponential function is a logarithmic function, and we'll look at those in a little bit. Or I think it's the next lesson that we'll be doing for put 2. That we'll look at the log functions. Okay, definition: an exponential function with a base a, f of x equals a to the power of x, where x and a are real numbers. A is greater than 0, and a cannot equal 1. Now, remember when we're talking about exponents in general, we have our base, and then we have our exponent, and that equals an argument. So if we do an example of 2 to the power of 3 equals 8, the 2 is the base, the 3 is the exponent, and 8 is the argument. Okay, a cannot equal 1 because 1 to the x is a constant function, does not show growth or decay. So if we start listing 1 to the power of 2, that's 1. 1 cubed is 1. 1 to the power of 4 is 1. Again, it continues on and on. So that is why a cannot equal 1. Also, a has to be positive because otherwise it could be imaginary. For example, if we have negative 2 to the power of a half, well, this is the same thing as a square root of negative 2. Remember that that half means a square root. And that could end up, or this is going to be imaginary. Or the other option is undefined. So if we have a to the power of negative x, which would give us 1 over a to the power of x. Again, A cannot equal 0 because this would become 1 over 0, which is undefined. So A has to be always positive, but cannot equal 1. All right, next what we're going to do is review exponents. And what we're actually going to start with, instead of starting with the negatives, let's start with 2 to the power of 0. Any number to the power of 0, we've already learned, is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Remember, it's 2 times 2 times 2. 2 to the power of 4, if you're not sure, we can break this down. We already said that 2 to the power of 3, or we already know what 2 to the power of 3 is. We just multiply that by 2. So 8 times 2 is going to be 16. So this is our, the fourth 2. So our answer for this is 16. Again, the same thing, once we have 2 to the power of 4, it's easy to calculate 2 to the power of 5. So we have that 2 to the power of 4 is 16. Now we just multiply that by 2. We've got 5 2s here. 16 times 2 is 32. Okay, now let's go back to the negatives here. So we've got 2 to the power of negative 1. Remember that that negative exponent flips it over, takes the reciprocal, so it's a half. 2 to the power of negative 2 is going to be 1, 2 squared, which is 1/4. 2 to the power of negative 3 is the same as 1 over 2 to the power of 4. No, sorry, that's not a 4. It should be a 3. 2 to the power of 3 is 8. So 1/8. Are you seeing a pattern here? We have the 2 here, a 2 here, 4, 4, 8, 8. So 2 to the power of 4 is 16. 2 to the power of negative 4 is going to be 1 over 16. Same thing here. 2 to the power of 5 is 32. 2 to the power of negative 5 is 1 over 32. Okay, so the key thing here is what we actually are doing, moving up and down. So when we are going down, what we did here is we multiplied by 2. That's what we do up here as well. So going down, we are multiplying by 2. So when we're, excuse me, when we're going up or towards the larger negative exponents, I should say, we're doing the opposite, which means that we are dividing by 2. And that's easy to look at over here. For example, 32 divided by 2 is 16. Here, on the other end, it's a little bit, or not as easy. If let's take 1/8 and 1/4. So what it means is that we are taking 1/4, dividing that by 2. Well, remember when we're dividing, we are changing it to a multiplication and taking the reciprocal, so a half. So top times top is 1, bottom times bottom is 8. And that's how we get that. So this is kind of the pattern that's going to be following, or that's going to be moving forward. Okay, rules for exponents. Some of these we've already covered also, so we'll do a quick review. 0 exponent, anything raised to the power of 0 is going to be 1. Doesn't matter if it's 2 to the power of 0, that's going to be a 1. 3 to the power of 0 is 1. Negative 3 to the power of 0 is going to be 1. Or if we have um, um, so yeah, let's look at one example where negative 3 to the power of 0. Notice that here the base is negative 3. Here our base is 3. So what this means is that this is negative 1 times 3 to the power of 0, right? So 3 to the power of 0, we already said that is 1. So negative 1 times 1 is going to end up being negative 1. So notice the difference again when the negative is outside or inside parentheses. What is your base? Okay, in general, m to the power of 0 is going to equal 1. Next is going to be negative exponents. Take the reciprocal of the base. So m to the power of negative 1 is the same thing as 1 over m. Let's look at some examples. 2 to the power of negative 2 is going to be 1 over 2 squared, which is 1/4. 3 to the power of negative 2 is going to be 1 over 3 squared, which is 1/9. Now, let's see what happens. So these are still easy. We've got whole numbers. Let's see what happens if we have a fraction. So 2/3 to the power of negative 2. What we do first is we want this exponent to become a positive, so we flip it over. 3 over 2 squared. Now, we can distribute the exponent here. 3 squared over 2 squared, which is 9 over 4. Okay, next, rational exponents. So we are taking the root, use the denominator as the index, use the numerator as the power. Um, so what does that mean? For example, if we have m to the power of 2/3, the denominator is the index. So it's going to be cube root of m squared. The numerator is the power. Okay, let's look at some examples here. Let's do, for example, 8 to the power of 2/3. So this means that we are taking the cube root of 8 and squaring it. So cube root of 8 is 2, and then we are squaring that 2, and that gives us 4. 16 to the power of half would just be a square root of 16. The 1, yes, to the power of 1, we just don't need to do that because it's going to be the number itself. 4 to the power of 1 is a 4. Okay, let's practice. So we have these exponential functions for the given values. So first, we have f of x equals 4 to the power of x. So what we're going to do is we're going to plug in the 3 where the x is. 4 cubed, that's going to be 64. 4 to the power of negative 2 is going to be 1 over 4 squared, which is 1/16. Let me actually circle the answers. Next one is 4 to the power of 3 over 2. That is, again, the 2 is the root, the index, and the numerator is the exponent. So square root of 4 is 2 cubed, which is 8. All right, our next example is going to be g of x equals 5 to the power of 2 minus x. Now notice that the 2 minus x is the exponent. So g of 3, 5 to the power of 2 minus 3. Well, we do that subtraction in the exponent first, so we get -1, and that becomes 1/5. Okay, next we have g of -2, so 5 to the power of 2 minus -2. Notice that there's two negatives back to back. 5 to the power of 2 plus 2 when we combine the two negatives. And then we have 5 to the power of 4, which is 625. Okay. The third one is h of x equals 1/3 x. We have h of -2, so 1/3 to the power of -2. Again, it's negative, so what we want to do is we want to flip it over. 3/1, that becomes a positive. Now, we have two options here. We can do 3 divided by 1, and we get 3 squared, which is 9. Our other option, and especially if it is not 3/1, what we would do is we would take out the parentheses and get 3 squared and 1 squared. And that gives us 9/1, which is 9. So the same answer, two different ways. Just depends on what your numbers are or what the fraction is. Okay, h of 3. So 1/3 exponent is 3. Again, we're dropping the parentheses, so 1 cubed over 3 cubed, which is 1/27. Okay, graphing exponential functions. F of x equals a to the power of x for all a that are greater than 0, and a cannot equal 1. Now, make sure that you are aware of this. A is the base, not the domain or range. So when we talk about the domain here, your domain is going to be all real numbers. If we go back and look at the sketches that we did here in the beginning, both of these keep going from -infinity to infinity. So they keep spreading out. So the domain is all real numbers. The range will be limited by the horizontal asymptote. So that will depend on the function. Now, exponential growth or decay, it is much more explosive than polynomial growth or decay. The variable is in the exponent, not in the base. So remember, an example of exponential function would be f of x equals a to the power of x. X is the exponent. Actually, you know what? Right here. If we do a polynomial function, that would be f of x equals, for example, x cubed. So now it's in the x is in the base. Okay, make sure that you're aware of that because that's one of those tricky things, and it confuses and also can make the whole thing wrong. So everything that's in here is important when we start graphing. Okay, what we're going to do here is we're going to look at exponential growth. So what do you notice about the steepness of the slope as the base gets larger? If we look at all of these, that we've graphed here. So our first one is 3/2x. Then we have 2 to the power of x, 3 to the power of x, and 10 to the power of x. So as the base gets larger, um, the steepness of the slope increases. So it increases, or we can write in other words, gets steeper as the base gets greater. Now, for this example, what we're looking at is base A that is greater than um, absolute value of 1. So it's a whole number that we're looking at here. 3 over 2 is the same thing as 1.5. So this is when we have exponential growth. Okay, now we're going to calculate each of these functions or values for each of the functions that define the graph. So what we're going to do is, hold on a second. Let's start with the y equals 2 to the power of x. We're going to do -2, -1, 0, 1, and 2. So we're going to calculate 5. Let's start from the 2. So 2 to the power of 2 is going to be 4. 2 to the power of 1 is a 2. 2 to the power of 0 is a 1. 2 to the power of -1 is going to be a half. And 2 to the power of -2 is going to be 1/4. Okay. Next, we're going to do the y equals 3 to the power of x. I need to make sure that, again, I don't cut in. Okay. So, same x's. And again, it's easier to start with the positive exponents. So 3 to the power of 2 is 9. 3 to the power of 1 is 3. 3 to the power of 0 is 1. And now we're going to start taking the reciprocal of what we already calculated. So 3 to the power of -1 is going to be 1/3. And 3 to the power of -2 is going to be 1/9. Okay, next we'll do the 10 to the power of x. Again, same x's, and now our y is going to be 10 to the power of 2, which is 100. 10 to the power of 1 is a 10. 10 to the power of 0 is still a 1. Any number to the power of 0 is 1. Now, 10 to the power of -1 is going to be 1/10. And 10 to the power of -2 is going to be 1/100. So you can see, even with the numbers like 10 to the power of x, well, that raises or goes up quickly when x is 2. Your y is going to be 100, where here for y 2 to the power of x, when x is 2, your y is 4. So if we start plotting these points now, notice something. They all have the 0, 1 point right here. So they all cross the y-axis at that point. That's your 0, 1. Now, so 2 and 4, 2 and 4 is somewhere here. 1 and 2 is going to be right here. And then we're going to start going closer to the x-axis right here. Actually, it's going to be 1 is here, and then the next point is going to be over here. Okay, what about the 3 to the power of x? Our first point is 2 and 9. So 2 and 9 is here. Next one is 1 and 3. So that's going to be right here. Then we have the 0, 1, and then we're going to get closer and closer to the x-axis right here. And then our 10 to the power of x, 1 and 10, 2 and 100, we're out of our scale because it only goes up to 20. And then 1/10, again, it's getting closer and closer to that x-axis, but it does not touch it. Okay, so that is your exponential growth. Now, let's look at exponential decay right here. That means that our base A is going to be less than absolute value of 1. So this means that we're looking at fractions. So what happens about the steepness of the slope as the base gets smaller? So 1/10, 1/3, half, 2/3. It decreases, gets less steep as the base um, now decreases as the base gets larger, actually. So if we want to answer the question gets smaller, that would mean that it increases, gets steeper as the base gets smaller. Okay, so what does that mean here? 1/10 is smaller than 1/3, right? 1/2 is smaller than or larger than 1/3. It's easy if you think about a piece of pie. If you split it into half, this piece is larger than if we take that pie and split it into thirds. Okay, so now let's calculate the values for these as well. We're going to go ahead and start with that half. Half to the power of x. So same values, and let's see what happens. Now, when we have the 0, that's, again, any number to the power of 0 is going to be 1. There's no changing that. If we do half to the power of 1, that's going to be a half. Now, if we do half to the power of -1, we flip it over, so we end up with 2. 2 over 1 is 2. A half to the power of 2 is going to be 1/4, because it's going to be 1, 2 squared. And then half to the power of -2, we're going to take the reciprocal of the 1/4, which is 4. Okay, so we end up at 0, 1 again. Then we're going to do -2 and 4, which is right here. -1 and 2 is right here. And then 1 is here, and 2 gets even closer to the x-axis right here. Can you guess which point they're all going to go through? The y-intersect is going to be 0, 1 for all of them, as you can see from the graph. Okay, let's do 1/3 to the power of x, and that is our y. Hold on here. X, y equals 1/3 to the power of x. So -2, -1, 0, 1, and 2. Again, 0, 1, 0, any number to the power of 0 is going to be 1. When we raise it, exponent 1/3 to the power of 1 is going to be 1/3. 1/3 to the power of -1 is going to be the reciprocal, so that's going to be a 3. 1/3 to the power of 2 is going to be 1/9. And 1/3 to the power of -2 is going to be the reciprocal of what we got for to the power of 2, so that's going to be a 9. Okay, -2 and 9 is going to be right here, -1 and 3 to right here. And then again, it gets closer and closer to the x-axis here. Okay, let's do the 1/10 to the power of x. Here we go. So -2, -1, 0, 1, and 2. Again, 1/10 to the power of 0 is going to be a 1. 1/10 to the power of 1 is going to be 1/10. 1/10 to the power of 2 is going to be 1/100th. Now, when we go to the negative, we're taking the reciprocal. So to the power of -1 is going to be 10, and to the power of -2 is going to be 100. Okay, we cannot graph that first one here because the 100 goes way beyond. So let's do -1 and 10, which is right here. Then it crosses that y-axis at 0, 1 and gets closer and closer to the x-axis. Okay. So let's move on. Patterns of transformations. So what we're going to do is we're going to follow the exact same pattern as polynomial functions. So this negative here reflects across x-axis. This negative h is our horizontal shift. Oops, I left an R. Horizontal shift. This k is our vertical shift. And our b here is the vertical stretch and shrink. Okay, so let's first graph the parent function. And if we look at these, all of them have a base of 3. So our parent function is going to be f of x equals 3 to the power of x. Okay, well, that sounds familiar. We actually have it right here, conveniently right here. So we already have the points. So we're just going to plug in those same points. We know that 0, 1, and then it goes 1 and 3, and then 2 and 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9 is somewhere here. And it comes down, so it comes down and gets closer and closer to the x-axis, never touches. Again, this point 0, 1 is one of the points that we want to make sure that we're aware of. Our horizontal asymptote for this is y equals 0, so the x-axis right here. Our domain is going to be -infinity to infinity, all real numbers. Our range, well, we have the horizontal asymptote, so that is from 0 to infinity. We're going up towards the positive numbers. Okay, let's look at this next example here. G of x equals 3 to the power of x plus 2. So we have that plus 2 here. That is our horizontal shift. And again, remember that this is a negative. So this is actually a negative 2, which means that it's going left 2. So what can we do? We can kind of move everything to the left 2. So this point 0, 1 is going to be moved 2 to the left, so it becomes negative 2, 1. And our next point here in this graph is 1, 3, and then we have our 2, 9. So we're shifting all those to the left. So the 1, 3 becomes negative 1 and 3. So negative 1 and 3 right here. And then 2 and 9 is going to be 0 and 9. And now we can graph the whole thing right here. Our horizontal asymptote is still the same. That did not change. Our domain, it keeps going to the left and the right, even though it's a steep increase up, but it's still, there's no restrictions on the right either. So it is negative infinity to infinity. And our range, we did not move it up or down, so that's still going to be 0 to infinity. Okay, let's look at this next one. H of x equals 3 to the power of x plus 2. So this plus 2 here means that we are shifting the parent function up 2. Okay, so our 0.01 here is going to go up 2. So it's going to end up in 0, 3. Same thing with 1, 3 is going to be 1 and 5. So 3, 4, 5 right here. Let me actually put that point over here. That's a 3. 1 and 5 is here. And then 2 and 9 is going to be way up. Now, when we shifted it up, our asymptote shifted up 2 also. So our horizontal asymptote is going to be y equals 2. So this graph here approaches and approaches that y equals 2, but never touches it. Okay, our domain did not change. That's still going to be negative infinity to infinity. Our range, again, this tells us kind of where we're starting or ending, depending on where the graph is. But it's above the x-axis, so this is the minimum. So 2 to infinity. Again, 2 is in parentheses, so that because it is not included. Okay, let's look at the next one. M of x equals negative 3 to the power of x. So what are we doing here? We are reflecting it across the x-axis. So all of these points, like the point 0, 1, is going to come down to down here. So that's going to be 0. Actually, that's going to be 0, negative 1. Our point 1, 3 is going to be 1 and negative 3. And our point 2, 9 is going to be 2 and negative 9. So that's going to be somewhere over here. Okay, so here's our, goes that way and that way. Now we can see that it approaches the x-axis, but never crosses it. So that is our horizontal asymptote. Our domain does not change. That's going to be negative infinity to infinity. And our range now, This is below the x-axis. So we start from negative infinity and it goes all the way up to 0. Okay? Now, next, we're going to go ahead and look at applications. So many real-life situations can be described using exponential functions, including population growth, people, animals, microbes, etc., growth of epidemics, radioactive decay, and other changes that involve rapid increase or decrease. Sometimes these changes are modeled using what we call the natural base, which is the irrational number e. Find e on your calculator. It is above ln and round the value of e to the power of 1 to 2 decimal places. So when you do e to the power of 1, it's going to be 2.72. What is the other irrational constant found on your calculator that we are more familiar with? That would be your, oops, sorry, pi. What approximate value do we round it to? 3.14, right? This is just to show that the e is a similar constant like pi is. Okay, now we're going to go ahead and look at a couple of formulas. So we're going to look at compound interest and then compound it continuously. If you need these formulas on the exam, they will be there, already given to you. All right, we first need to figure out what does all this mean. So A is the interest. Um, or hold on a second. That it's not the interest. It will be how much money is in your account. Sorry. So A tells us how much money will be in your account. P is the principal. R is the interest rate. And this is always a decimal. It's given as a percentage. We have to convert it to a decimal. N is the number, how many times we've compounded in a year. And T is the time. Again, A is how much money. How much money you have in the account at the end of the time. Okay, so let's look at an example here. If you are given $10,000 by Auntie Gerda and decide to invest it at an annual rate of 5.5%, how much money will be in the account after 5 years if it is compounded monthly? Okay, $10,000 is our principal. That's the money that we are given. Annual rate is 5.5%. So 5.5%, we need it as a decimal. We divide it by 100. So we move the decimal 2 places to the left, 0.055. Time is 5. And compound it monthly. So how many months do we have in a year? 12. Now we're going to plug it in, since it is compounded monthly, into this first formula here. So A equals $10,000 times 1 plus R over N, so 0.055, that should be a point, divided by N, which is 12, to the power of N times T. Our N is 12 and our T is 5 years. Okay, now if you are plugging this whole thing in the calculator, make sure that you're careful with the parentheses. So, for example, this part right here, the calculator, um, you're going to have to make sure that either you have parentheses here or you do that multiplication first, 12 times 5. And keep all the other parentheses as they are. Now, when you do the calculation, we get $13,157.04. So that is how much money will be in the account after 5 years when it is compounded monthly. Okay, let's look at compounding quarterly. So everything else stays the same. N is the only thing that changes right now. So quarterly, there's 4 quarters in a year. So A equals $10,000 parentheses 1 plus 0.055 divided by 4. That's where it changes to the power of 12 times 4. And when we do this calculation, we get $13,140.67. Notice the difference already with those amounts. I mean, it's $17, but still. Um, so let's look at this last one, compounded continuously. That is when we're going to use this one right here. Again, our P is the same $10,000. That hasn't changed. Our R is 0.055 again, and our T is 5. So A equals $10,000, which is our P, times E to the power of 0.055 times 5. And again, the same thing as I said previously, make sure that if you're plugging this whole thing in the calculator, you put that multiplication inside parentheses. Otherwise, the calculator is going to think that you're only raising the e to the power of 0.055 and then getting that answer and then multiplying by 5, not that you're multiplying the 0.055 by 5. Okay? So when we do this calculation, we get $13,165.31. So the more we compound, the more money we're going to get. All right, next example. The annual amount of energy produced in the United States from dry natural gas in trillion cubic feet can be approximated by the function g of t um, equals 14.66 times 1.042 to the power of t, where t equals 10 corresponds to the year 2010. And now notice this is trillion cubic feet. We are supposed to find the amount of dry natural gas energy produced in 2000. So if t equals 10 is 2010, then 2000 is going to be t equals 0, right? So we're going to plug in that 0 where the t is 14.66 times 1.042 to the power of 0. Well, that's going to be, this whole thing is going to be 1 because it's to the power of 0. So we end up with 14.66. And now remember the trillion cubic feet as the unit in your answer. Okay, next one. Find the amount of dry natural gas energy produced in 2015. So if 2000 is 0, then 2015 is going to be 15. G of 15 equals 14.66 times 1.042 to the power of 15. That ends up being 27.17 trillion cubic feet. And then, if the model continues to be accurate, project the amount of dry natural gas energy produced in 2022. T, this time equals 22. So G of 22 equals 14.66 times 1.042 to the power of 22 equals 36.24 trillion cubic feet. Okay, that's it for this lesson. Let me know if you've got any questions about it. Bye.